In this lesson, we're going to study two unique features of rational functions. We're going to be looking at vertical asymptotes and holes. Now, remember, a rational function is a fraction, and you learned back in middle school that the big no-no with fractions is you cannot divide by 0. So if you tried to type this in your calculator, 1 divided by 0, you get an error. 1 divided by 0, 2 divided by 0, 3 divided by 0, even 0 divided by 0. It's just not possible. So a vertical asymptote is what happens when the denominator is equal to 0. If you try to divide by 0, you're going to end up with a vertical asymptote. Now, there is one caveat to that. If the factor cancels out, instead of a vertical asymptote, you're going to be left with a hole instead. For example, look at the graph down below. This is the corresponding equation. So this equation here on the left is going to produce this graph here on the right. And in order to end up with this vertical asymptote and in order to end up with this hole in the graph, you have to look at the denominator. The big no-no with fractions is you're not allowed to divide by 0. So see this first factor? If I set that equal to 0, and solve for x, so I would subtract 1 on both sides. We end up with x equals -1. Plug in -1. -1 plus 1 is 0, and you can't divide by 0. That's going to pose a problem when you graph it. Same thing is true with the other factor, x minus 3. Set that equal to 0. So here I would add 3 on both sides. I end up with x equals 3. Plug it in. If you plug in 3 minus 3, you get 0, and you can't divide by 0. That's going to create something weird on the graph. So then the question becomes, okay, so you have something weird going on at -1, and you have something weird going on at +3, but how do you know if it's an asymptote or whether it's a hole in the graph? Look at the top. So notice at the top of our function, we have an x plus 1, and on the bottom, we also have an x plus 1. Well, we know that anything divided by itself cancels out. So that error that we had at -1, you literally removed it from the graph whenever you canceled those factors out. That's what creates the hole. Whatever's left over, that's going to make your vertical asymptote. So one more time here, the big idea is 0. You're not allowed to divide by 0. So whatever you've got at the bottom of the fraction, you set it equal to 0 to find out where you're going to have issues with your graph. Anything that cancels out is going to leave a hole, but the one that doesn't cancel out is going to leave you with a vertical asymptote. Let's take a look at a few more examples. Example 1, we've got x plus 3 over x squared plus 2x minus 3. The very first thing I'm going to do is I'm going to come over here and I'm going to factor the top, I'm going to factor the bottom, I'm going to factor anything that can be factored. So on the bottom, I've got 3 terms, so I'm looking at this thinking what multiplies to -3 and adds up to 2. So I'm going to have x plus 3 and x minus 1. On the top, I just have an x plus 3. There's no GCF there, so I'm just going to bring that over. Now I'm looking at the top and the bottom, and I see an x plus 3 on top, and I see an x plus 3 on bottom. Anything divided by itself cancels out. So that's going to leave us with 1 over x minus 1. Now remember, the big idea is you cannot divide by 0. So whatever's left over on the bottom, this is going to create a vertical asymptote at whatever point would make this 0. So I'm going to take that, I set it equal to 0, I get x equals 1. And you can check yourself here. If you plug in 1, if you put a 1 right here, 1 minus 1 is 0, and you cannot divide by 0. So that's going to be our vertical asymptote. But if you back up one step, there was something else in the denominator also. That x plus 3 was down there. Since it got removed from the graph, this is going to leave behind a hole. So again, I'm going to set this equal to 0. It's all about 0, and that gives me negative 3. Right? If you plug in 3 plus 3, you get 0, and you can't divide by 0. Now here's the only difference with a hole. A hole is an actual point, and a point has an x-coordinate and a y-coordinate. So we've established here that our x-coordinate is negative 3, but we still need to know what the y value is. So like you've done in previous topics, if you find out an answer for x, all you have to do is plug it in to figure out your solution for y. So I'm going to go all the way over to the end after we've canceled this thing out, and I'm going to plug that negative 3 in right there on the bottom where the x is. So it'll be 1 over negative 3 minus 1. So that would be 1 over negative 4, or negative 1/4. So the hole in my graph happens at negative 3, negative 1/4. Example number 2. We've got x squared plus 7x minus 18 over 3x minus 6. Again, we're going to start by factoring because what we're really doing here is looking for anything that might cancel out. So on the top we have 3 terms. I'm asking myself, what multiplies to negative 18 and adds up to 7? That's going to be x plus 9 and x minus 2. On the bottom I just have 2 terms. So I'm looking at the GCF here. They're both divisible by 3. So I'm going to factor out a 3. And if I factor out a 3, that leaves behind x minus 2. Right away, we notice that we have an x minus 2 on top and an x minus 2 on bottom. That part's going to cancel out, which leaves us with an x plus 9 on top and just a plain old 3 on the bottom. Now, remember, the big idea is you cannot divide by 0. Well, if you look at the final answer over here, you have a 3. There's no x, it's just a 3. No matter what number I plug in for x on top, it's always going to be a 3 on bottom. So the vertical asymptote here is none. There's no way that we can divide by 0 because it's always going to be dividing by 3. So I'm going to say none for the vertical asymptote. I'm going to say because there is no x on the bottom. There is no x left on bottom. However, if we back up one step, there was something down here in the bottom that we canceled out. That's going to be our hole. So the reason why this is a hole is because when we cancel it out, it literally removes that point from the graph and leaves a hole. So again, the big no-no is 0. So I'm going to set this equal to 0. So we end up with 2, right? If you plug in the 2, 2 minus 2 is 0, and you cannot divide by 0. Now remember, a hole is an actual point. It has an x value and a y value. So we've determined here that our x value is 2, but we still need to figure out the y value. So what we're going to do is we're going to take that 2 and we're going to plug it in for x. So that would be 2 plus 9 divided by 3. So 11 over 3. That's where I would find a hole in my graph. All right, just a few more here. We've got x squared minus 4 divided by x squared minus 2x. Up top, this is a unique factorization here. You'll remember from the last unit. You should recognize this as difference of squares. So when we're factoring this, we want to know what do you multiply together to end up with x squared minus 4. It would have to be x times x. And remember that 4 is a perfect square. Square root of 4 is 2. So we would have x plus 2 and x minus 2. All right, on the bottom, we have x squared minus 2x. Here, we can factor out a GCF. If you notice, both of these terms have an x. So if you factor an x to the front, that would leave you with x minus 2. Now we notice here that we have an x minus 2 on top, and we also have an x minus 2 on the bottom. Anything divided by itself is going to cancel out, which leaves us with an x plus 2 on top and just a single x on the bottom. Now, remember the big no-no with fractions is you cannot divide by 0. Weird things happen when you try to divide by 0. So if you look at the very end, I'm going to take that x that's left over, this is going to be my vertical asymptote, and all I do is set that equal to 0. I don't even have to solve anything this time because it's just x equals 0. If you plug in 0, you can't divide by 0. It's going to create a vertical asymptote. Back up one step, there was another problem here, the one that we canceled out. If we set that equal to 0, we end up with a 2. So imagine plugging a 2 here for x. 2 minus 2 is 0, and you can't divide by 0. The only difference is this point actually got removed when we canceled it out, so it's going to leave a hole in the graph. Now remember that a hole is a point. It has an x-coordinate and a y-coordinate. So we've established here that x is 2, but we still need to figure out what the y is. So to figure out what y is, we're going to just go plug this in. So I'm going to plug in that x equals 2 on the top and on the bottom. Anywhere where you see x, you're going to plug in a 2. So we're going to have y equals 2 plus 2 divided by 2. That's a lot of 2s. So 2 plus 2 is 4. 4 divided by 2 is 2. That is a whole lot of 2s. Get it? A whole lot of 2s. At last example, x plus 1 over x squared plus 3x minus 18. We're going to start by factoring. On the bottom we have 3 terms, so I want to know what multiplies to negative 18 and adds up to 3. So that's going to be x plus 6 times x minus 3. On the top you have 2 terms, but there's nothing that those have in common, so we're just going to leave it as x plus 1. Notice that nothing at all cancels out on this problem. So that means there cannot possibly be a hole. A hole only occurs when you remove something, when you cancel it out from your equation. So since we didn't cancel anything out, we do not have a hole. So I'm going to say hole because nothing cancels out. But we do still have some stuff in the denominator. In fact, we have 2 factors in the denominator. Remember, the big rule is you cannot divide by 0. So I'm going to take the x plus 6 and I'm going to set that equal to 0. It's going to give me x equals negative 6. Right? If you plug in negative 6 here, negative 6 plus 6 is 0, and you cannot divide by 0. I'm going to do the same thing with the other factor. So I'm going to take this and I'm going to set this equal to 0. That's going to give me a positive 3. Same idea, if you plug the positive 3 in right here, 3 minus 3 is 0, and you cannot divide by 0. Since neither one of these cancels out, there are 2 vertical asymptotes.